So, good morning students, and let us, in this session we continue our discussion on the noise. Noise as a parameter that should be taken care of while we design an operational amplifier. Okay. So as I said, we have a power supply noise, we have an input signal noise, and we have a noise generated by the devices. So even if there is no input signal noise, there is no power supply noise, still I have a kind of a noise present in my output, which will be coming as a distortion. So if you do the FFT, or if you plot the Fourier series, or FFT, if you take fast Fourier transform of your signal and you plot the magnitude spectrum, you will get, apart from the fundamental, many harmonics appearing, so that we know that depending on the magnitude of harmonics present, we can say how much noise is there in the circuitry, and we compute that distortion of the signal in terms of, remember, total harmonic distortion, a factor which we call as a THD. So how many harmonics are present which are corrupting the signal? Because my sinusoid should be a pure sinusoid. If it is not a pure sinusoid, that means there is a corruption happening. Signal is getting corrupted. Okay. So very easily it can be get by doing the simulation analysis while running the circuit simulation. But that gives me an idea. Now specifically for noise, we look at the signal to noise ratio. Very common performance metric which is used for analyzing the noise behavior of the circuit. Now as we say that noise is a random signal, and it is because of a physical phenomena, that is because of the random thermal motion of charge carriers which cannot be removed. So noise cannot be removed at all. We cannot remove the noise, but we can only limit it. We can design in such a way that it can be limited. Okay. Now remember, the op-amp which is critical for noise can be designed at different frequency ranges. So in RF range, the design will become entirely different because of inductive parameters coming into picture. Whereas in the frequency range in which we are operating, we are assuming there are no inductive effects. There are no inductive effects. As a result, we are only taking resistive and capacitive effects. Okay. So the design procedure entirely changes when you move from one frequency range to other frequency range. So in RF frequency range, the designing is a bit different. There we make use of the S parameters in order to do the designs. Here we are not looking for the S parameters. We are working with our normal H parameters. Remember H parameter model or Z parameters. You can work with any modeling, either impedance or admittance parameters or hybrid parameters you can use. But S parameters we do not use. S parameters are used only in RF ranges. Radio frequency. When you work at radio frequency ranges, specifically you are designing for radio frequency frequencies. Now, by looking at the noise at the output, what we do is usually we reflect that output noise back to the input by dividing it by the gain of the circuitry. Okay, so this is called as the input referred noise. Input referred noise. Now I can represent, as I said earlier, noise in terms of voltages or currents. Because in electrical circuit there are only two parameters. So for my convenience, though I know it is going to be a random signal, but I give it some shape so that I can understand it very conveniently. Okay. So we say, okay, input referred noise voltage or input referred noise current. Okay. And then if it is a voltage, then I say, okay, if my signal is say 20 millivolt and noise is say 1 millivolt, so signal to noise ratio will be 20:1. Okay, I should not have noise voltage comparable to signal. In that case, my noise signal will get drowned in the noise itself. Then my op-amp will not know which one is the actual signal, which one is the noise signal. In that case, output will be highly noisy, very, very corrupt signal, and we will not be able to get something meaningful out of that output voltage. So that is why we look at the SNR at the input, and also we look at SNR at the output. We also always look at that also. So signal to noise ratio, so normally if you do not give any differential signal, no signal is provided to the circuitry, and even then you are getting an output, a differential output. Again remember, it is not because of power supply noise, it is not because of noise coupled to the input, it is not because of offset. It is not because of offset. We assume that everything is 0. In that situation, whatever signal you are getting at the output is the noise output. That is because of the random currents generated by the moving charge carriers at room temperature. That is because of the noise generated by the device voltages. So we have two types of noise, two terminals at which we compute the noise: output referred noise voltage and input referred noise voltage. So input referred noise is nothing but the output divided by the gain of the circuit. Now, in order to understand the noise behavior, we have to first develop a statistical model of the noise. Because noise is something random, if you simply take its average, its random fluctuations will call it to go to 0. So we try to get it in terms of a useful quantity. We want to understand this noise signal so that we can understand it more meaningfully. And we do it by finding its power. We compute the noise power. We compute the noise power. So noise power is something that is, you take all the fluctuations, you simply square them so that all fluctuations become positive, and then we take the integration of that. We simply take its integration and then divide it by the entire time over which we are observing the noise signal. So that is giving you the power of the noise signal. That gives you the power of the noise signal. Now, noise is also has a frequency behavior. Noise is not same for all frequencies. So if I change my input signal frequency, noise value keeps on changing. That is if I try to plot this noise power for different frequencies, I will get a noise power density spectrum. And it will not be constant. It will not be constant because there is a noise component which is dependent on frequency of the input signal. Okay, so we generally plot the power spectrum, power density spectrum of the noise signal. We always plot it like that. So once we compute the noise power, maybe I can refer it in terms of voltage, or it can be referred in terms of the current. And once we have done that, then I plot its power spectral density with respect to the frequency. How do you get this plot? So what I do is that I set my input voltage at a particular frequency. At that frequency, I observe the noise at the output for a long duration of time. For a very long duration of the time. Okay? And in that, so my frequency range is, nominal value is that frequency, say 1 megahertz, and then plus minus half megahertz. So in a range of 1 megahertz. 1 megahertz plus 1 unity. For that range of frequency, I observe the power of the noise. I observe the noise and compute its noise power, and that noise power I plot with respect to 1 megahertz. I repeat this process for various values of the input signal frequency. So 1 megahertz, then say 2 megahertz, then say 3 megahertz, then 4, or you can change the step also, 1.1 megahertz or 1.2 megahertz. It depends on you how many points you are taking in between. But you keep on repeating this process every time for every nominal frequency with plus minus half hertz. That is in the range of 1 hertz. Around the nominal frequency, we repeat this process, compute the noise power, and then plot. And this is what we observe. We get a power spectral density. So at F1, this may be the noise power, plus minus half of hertz. In a range of 1 hertz around the nominal frequency. This is F2, again repeat the same process. F3, again repeat the same process. Fn, again repeat the same process. And then you plot it, we get a power spectral density. This is something which is very very useful to us. It gives me the noise power at different frequencies of the input signal values, input signal frequency values. Now this is something that I have and I would be using it in my design analysis. So this gives you a very clear idea how does noise varies with respect to the frequency. Now before we start analyzing the circuits, this is how we get the spectrum. This is just what I have just explained. Okay? And then remember what are we doing? Band limiting. What is this band limiting? What is it doing? It is setting a range of 1 hertz around the center frequency or the nominal frequency. We are doing band limiting of the signal so that value remains within 1 hertz around the signal frequency. Okay? And once you are done doing the band limiting, then you are squaring the fluctuations, and then you are simply getting all the, you will either you get the square values or simply take the average, or simply take the root of that. Either simply mean square average or simply root mean square average. Clear? Which any way you can work with. You can work with square values also. But then keep in mind your unit will become accordingly voltage square per unit hertz. Because it is 1 hertz frequency range variation. Unit will accordingly change for the noise power. Fine, so once we have done that, now we come to the origin of noise. What phenomena causes noise? What are the different ways in which noise can be generated or originated in devices? First component I have just told you, it is random thermal motion of the carriers. Because carriers are never at a static in a state. They keep on moving even if there is no voltage applied. And wherever charge moves, that is equivalent to a current. As a result, we get a noise generated in the circuit. So random thermal noise, random thermal motion, or the noise generated is simply called as a thermal noise. This is the thermal noise. And how do we estimate? So people, they have done, so suppose that there is a resistor in our circuits, we have resistor coming up. So we will try to find the statistical model for each and every component. So let us take the resistor first. If I take the resistor first, then I have to understand how much thermal noise power will come out to me. What is the thermal noise power? How much thermal noise power will be generated if there is a resistor present in the circuitry? Clear? So we assume that resistor, now I can either model it as a voltage or it can be modeled as a current. If you model the noise as a voltage source, then I have to put that voltage source in series with a resistor. Then I say noise generated in the resistor is simply Vn square average. I am not taking square root. Vn square average. Okay, which is, how do I represent? I say it is in series with the resistor, where I am taking resistor noiseless. It is as if there is a voltage source which is generating the noise. This is how I am representing the noise, thermal noise in the resistor. I assume my resistor is a noiseless and there is a voltage source which I represent as Vn square average. Remember, this Vn square average may not have any polarity. Polarity is immaterial. In analysis, we always add all the noise components. We always add. We do not go by polarity because we do not know whether it is plus or minus. So though you show the polarity, it is immaterial. We do not take that polarity into account because after all the noise components are added at the output to get the worst case value. Always remember that. So this does not have any polarity. Vn square average source does not have any polarity. Always remember that. Okay? And what people they have done, they have observed the noise through this resistor for a long duration of time at a certain frequency, and they plotted the power spectral density of this noise. Okay? As a result, they found that this component Vn square average per unit hertz, remember, it is per unit hertz, it does not change with frequency, it is constant. It is also known as a white noise. Remember, This is also called as a white noise, and they found that its value, we will not go into derivation, I am simply using their result, all the what physicists they have already done for me, that this value depends on the Boltzmann constant K, the temperature T, and the resistor value R multiplied by 4. 4 kTr. Clear? This is represented by the expression 4 kTr. So if I represent Vn square average as In square average, I simply change its location to parallel combination. Instead of series, I represent it as a In square average in parallel. A current source, again direction is immaterial. Though you show a direction, but it is immaterial. Clear? So In square average, and I can represent In square as simply Vn square average by R square. Simple. My normal relations for the V and I characteristics. So In square is simply Vn square average divided by R square. Divide by R square. So whatever Vn square average we had, 4 kT R, so that is divided by R square. 4 kTr, that is divided by R square. So you get In square average as 4 kT by R. I will be using these values for analyzing my noise performance of my circuits. Clear? So thermal noise representation is now with me for a resistor. Now in our components we can have MOSes. We will have MOS transistors also. We will not have inductive components. Okay? So we come to 4 kT by R. That is a MOSFET noise. Again in MOSFET, what can cause noise to originate? So first is the channel. Channel is a source of conduction. Channel is a region in which the carriers move. Because the free carriers over there may not be constant. They keep on moving through the channel because of random thermal motion. So MOSFET has a thermal noise component. A MOS has a thermal noise because of random variations of carriers through the drain source region and through the channel. Again, the same thing is done. The noise is observed for the MOSFET, and then it is again power spectral density is plotted, and we represent the MOSFET noise either as a MOSFET which is noiseless in series with a V thermal square average, or in parallel with a current source value is maybe I noise which is thermal square average. We are developing a model for us so that we can use it while doing our analysis. So the thermal noise current for a MOSFET is given as, now the value, look at the expression which has been derived, given as 4 kT gamma GM. Gamma is a parameter which is a noise dependent parameter, and for a long channel MOSFET its value is 2 by 3. Again for a short channel MOSFET it has a different value. So this was already derived. I simply use that expression. In square average is given as 4 kT gamma GM. So what will be Vn square average for a MOSFET thermal noise? It would be 4 kT gamma GM into, no, you multiply it by, okay, this is the noise current that will be generated in the voltage, in the, yes, correct. It's okay. So we are getting 4 kT gamma GM In square average noise current, thermal noise current through the MOSFET. Another source of noise in MOSFET is a flicker noise. Remember, thermal noise is independent of frequency. It is a white noise. Its spectrum is constant throughout. It doesn't change. Now we come to the flicker noise. That is because of the dangling bonds that we have at silicon dioxide interface. That means that falls under the channel region. That region falls into the channel region. silicon dioxide interface. Please look at the slide. Wherever you have a gate, just below it you have a silicon. And because silicon abruptly stops there, and then we have a growth of silicon dioxide. We have a growth of silicon dioxide. So because of the lattice being incomplete at the silicon dioxide interface, so these energy states, which are the vacant positions just near the interface, they have a tendency to capture an electron and release an electron at random. Because they are free energy states. Lattice is incomplete over there. Free energy states are available, and there you have the free carriers present in the channel. They may get trapped into these energy states and may get released through them at random. It is a random process. As a result, because of this random trapping and releasing phenomena, we get a net current flowing through the channel, which is a noise current. Again, so this is known as a flicker noise. This noise current is because of the noise. We call this as a flicker noise. So we have a current originating into the channel because of thermal noise, or a current originating into the channel because of flicker noise. Now this flicker noise has a frequency dependence. This flicker noise has a frequency dependence. Okay, and we get this value as simply IN square flicker. Average as simply K, which is a flicker noise coefficient, GM square by Cox WL into F. This is a current produced, noise current produced in the channel because of these trapping phenomena, random trapping phenomena of the carriers in the dangling bonds at silicon dioxide interface. So if I represent it as a voltage source, I simply divide it by GM square, which gives me this. Because current through MOSFET is simply GM VGS. Current through MOSFET is simply GM VGS. So if my current is noise current, so VGS will be noise voltage. VGS will be noise voltage. So simply if the current is known to you divided by GM square, you will get the noise voltage. So either represent MOS as a noiseless component and represent a VN square flicker average in series with it, or represent the noise as a current source in parallel with it. Then we say that our component is noiseless, but there is a voltage or a noise voltage or a noise current source. We represent it like that. Now I have all the components with me, how much noise voltage and how much noise current. I have all the components with me with which I can start my analysis. But before that, if I say in a MOSFET total noise, if I plot the power spectral density of the total noise is composed of the flicker noise and the thermal noise. The flicker noise and thermal, if I plot the power spectral density, then because of F coming into picture, so at low frequencies, flicker noise dominates. Because frequency comes in denominator. So at low frequencies, the flicker noise dominates. At high frequencies, the thermal noise dominates. As a result, we get a knee point which is called as a noise corner. Or 1 by F corner. This is the knee point where we say that one point at which the flicker noise is equal to the thermal noise power. Flicker noise power is equal to the thermal noise power. Beyond that, 1 by F, flicker noise will be very less. Before that, thermal noise will be very less. This is known as the 1 by F corner. This is called as the 1 by F corner. So here At this corner, the two components are equal. Noise current because of flicker and noise current because of thermal. I will equate them together at 1 by F corner. So when you equate them together, I will get the expression for the frequency which is known as the corner frequency. The frequency at which the two components will be comparable. I will get this as a corner frequency. So at what frequency both the noise will exist? Both the noises will exist in a MOSFET. I can obtain that expression. So for frequencies more than this FC, I will not compute flicker noise because it would be very less. I will only compute thermal noise. And for frequencies less than FC, I will only compute flicker because then thermal noise will be less. But for frequencies at equal to FC or comparable, I will compute both the components to get a meaningful result at the output. To get a meaningful analysis for the noise performance. That is why we compute this FC. Clear? Now once we have got this expression, all the expressions with me, let us start computing the noise. As I said, if you cannot remove noise or if you cannot remove a certain problem, at least first of all estimate it. Estimate it, find an expression of it or try to model it and then try to see what you can do to minimize it. This is how we tackle any problem. If something you cannot remove which is problematic, at least first of all try to estimate how much it is going to come to, so that develop a model or an expression for it, and then from the expression try to find out what can be done to minimize it. That is what we are going to do also here. Same thing. Same is for PSRR, same is for CMRR. We look at values, what can be done to increase CMRR, to increase PSRR. Here also we will look at ways how can we increase SNR. How can we increase SNR? Signal to noise ratio. What device changes we can do, not what design changes we can do in order to improve the SNR. So, start with the normal, very simple common source amplifier with resistive loading. Got it? So till date we have not done, till now we have not done any analysis. We were just developing models for us, expressions for us which will be useful for us in analysis. Clear? Pilani campus? Goa campus? Clear? We are not getting any answers from Goa campus? So now we start calculating. So I should know how much noise output will come at a CSA output when it is a resistively loaded. Since there are two components, I am assuming VSS, VDD is not generating any noise. And there is no noise input signal also. Okay? So according to me, there is no input signal noise coming into picture. So I will say there is no, it is behaving like a AC ground, as if I am not giving any signal. Now it is a noise analysis. So we are working in terms of noise voltages or noise currents. So there is no noise voltage at the input because input signal is not having any noise. So for me it is like a AC ground. This behaves like a AC ground. Look here. Because input signal is not containing any noise component. Okay? So if there is no noise signal at here, it is behaving like an AC ground for me. And resistor will have a noise component. MOS also will have a noise component. We represent both the noise components in terms of currents. So it is RD, which is noise, in parallel with a noise current, which is IN square average through RD. RD, which is my resistor, load. Similarly, I represent it by a noise current in parallel with MOSFET M1, represented by IN square. It is M1, so 1 square average. Both are generating noise currents. Both are generating noise currents. If you want to work with V, I don't mind. But then some way has to be, result should not vary. So both are generating noise currents. As I said, direction is immaterial because ultimately all effects are going to be added up at the output. Though we represent noise current, we hardly make use of. Hardly we represent direction. But we don't make, because ultimately every component we compute and then we add. Okay? So once we have, so as a result I will get a Vn square at the output. Vn square average will come at the output node. A noise voltage will appear at the output. So we will do by our normal analysis method. We all know small signal analysis. Because now one more thing, these noise sources are not correlated to each other. MOS noise source and the resistor noise source, they are not having any relation between them. They are not correlated. Their noise generation is not dependent on each other. It is a random process independently happening. So they both are uncorrelated sources. There is no correlation between them. I hope you all understand what is the meaning of correlation. As a result, the total effect will be added. Total effect will be added at the output. So total noise power, average value will be addition of both the noise powers. Simply because of this, no correlation happening between the two sources. We simply go by this. So we compute the output noise which is generated at the output node. Remember, this is per unit hertz. I told you this is per unit hertz. Okay. So now I represent. So total is very easy. A noise current here and a noise current here. You can use the method of superposition or whatever way you want to use. Compute the voltage at this point because of this IN square RD. Compute the voltage at this point because of IN square 1 average. So what is this component coming out to be? Tell me, do the analysis, small signal analysis, everybody knows how to do. Take only one source at a time. Other source can be open. Make it open source. Make it open source. Find the contribution at VN out. Similarly, take another current source. Find the contribution at VN out. And then add the two effects together. Expressions are known to you. IN square RD expression is known to you. Expression for IN1. IN1 is summation of the two. Thermal plus flicker. Kindly do it. Goa campus also students, please do it and tell me the results. Take one source at a time. Open source other. Find the net output voltage. MOS RO you may take some value or you may treat it as infinity. There would be RO of the MOSFET also. But remember, MOS will be GM VGS. What will be VGS? Can you tell me? 0, because gate is AC ground. You can model the MOSFET as GM VGS current source in parallel with RO. First assume there is no RO. RO is infinite. What is the value for VN square R out? When there is only IN square RD. Are you able to do it? Can you do small signal analysis? VDD will be AC ground, remember? parallel analysis. Same way as we have been doing till date. Yes, Goa campus, are you able to get the concepts? So what will be Vn square out average? Tell me. It would be total current. So it would be simply In 1 square average plus In RD square average dropping across RO parallel RD. What is In 1 square? Total value. Give me the expressions. Give me the 4 kT. 2 by 3. So there are two values, thermal noise and flicker noise. So it is nothing but 4 kT 2 by 3 GM. GM1 because there is M1 plus what is the thermal noise component? Okay, this is thermal. This is thermal. What is the flicker noise component? K flicker GM1 square divided by C ox WL into F. W1 L1 for M1. This is the total plus one more In square RD. So 4 kT. No, for this one. 4 kT by R. 4 kT by RD. It would be RD. This whole thing dropping across RO parallel RD. Whole square. It has to be square because this is square. So this component must be also square. This is nothing but per unit hertz. This is per 1 hertz. Vn out square, noise power at the output node per unit hertz. And if RO is infinity, this will become simple RD square. This would become simple RD square. So this is what we have. Look at the expression on the slide. Has it not come? Okay. Now this is your noise power at the output as square average value per unit hertz. So when you reflect it back to the input divided by the gain of CSA, divided by the gain of CSA, that gives you what? Input referred noise voltage Vn square in average. Vn square in average. In input terminal. Now you can compute this value because GM is known to you, RD known to you, Boltzmann constant known to you, T temperature of room temperature is known to you. I can compute this value and then I compare it with input signal. Either you take a square root of it or you double the or square the input signal. Because if you find SNR, you have to take the ratio of input to noise. The ratio of input to the noise, input signal voltage divided by the noise voltage. So noise voltage we are getting Vn square in. So take its square root. Take its square root and then take the ratio. That gives you SNR at the input. That gives you signal to noise ratio. Signal to noise voltage ratio at the input and at the output. Now if SNR is good, then I will say my signal value is more than the noise value. So there is no chance of noise getting drowned into the noise. there is no chance of noise getting drowned, then output will be able to detect the input signal out of noise and it will produce a meaningful result at the output. Signal to noise ratio is good. Or this also gives me, alternatively, I can use this noise floor. Gives me the minimum signal that you should give to the amplifier so that it does not get drowned into the noise. So if the noise floor or noise voltage comes out to be 10 millivolt, then your signal should be more than 10 millivolt. That gives you minimum detectable signal. Minimum detectable signal value for MDS. That your signal you should not provide less than 10 millivolt, rather it should be more than that. Otherwise, noise circuit will not be able to understand which signal is noise, which signal is the actual signal. So this gives you the minimum value. That is the limiting. I certainly should not have signal to be equal to 10 millivolt because 10 millivolt is my noise. But that gives me an idea. That gives me an idea that input signal should be more than the minimum detectable signal. Now what can you do to reduce the noise voltage? Can you do something? Now look at the expression. Can you do something to reduce the noise? You should increase GM. You should increase GM and you should also increase RD. That's what expression tells me. Nowhere I am writing per unit hertz, but it is implicit, remember. Wherever Vn square average is coming, it is always per unit hertz. Always. Okay? So I should work, larger the GM, less will be the noise. Larger the RD, less is the noise. So if your noise components are coming too many, your signal is getting too much distorted. Not because of PSRR, not because of CMRR, but because of this only, then try to work with larger GM and larger RD. It will bring down the noise floor. Similarly, we can do the analysis for a diode, for a actively loaded circuitry. Where you do not have RD, you have a PMOS acting as a load or current mirror acting as a load. Again, there are two MOSFETs now, one NMOS and one PMOS. Then it is only MOSFET noise which will come into picture, but every MOS will generate a noise current. Every MOS will generate a noise current. You can again draw the model. These will be AC ground. This is also AC ground and this will also be AC ground. Again, get the expression and find out the total value of the noise generated. Now they have done the analysis only for thermal noise. They have done the analysis only. Look at the expression, it is only for thermal noise. Maybe for frequencies more than FC. For frequencies more than FC, or you can do it for all the values. For both flicker as well as the thermal. So now if you want to reduce this noise, what should you do? Compute Vn in square. Vn in square. This is in. This is in. What is in means? Divided by the gain value of the differential pair, gain square, because everything is coming in square. So divided by the gain square. GM RO parallel RO, it would be there. So this is input referred noise voltage for the actively loaded CSA. Actively loaded CSA. Only for thermal noise. Only for thermal noise. Now gain depends only on GM square, GM1 square. So in the denominator you are getting GM1 only. So what should you do to minimize the gain or minimize the noise? Increase GM1, reduce GM2. If noise is coming too much, try to work with a larger GM1 and smaller GM2. Do this analysis for, okay, let us, before we start going for cascade or differential. Now, how does the frequency response change? Now, every circuit has a frequency response. Every circuit has a frequency response. So, gain changes with frequency. So, input referred noise voltage will change with frequency. Why? Because it is divided by gain. It is divided by the gain. So, if I assume for simplicity that circuit has a single pole response. If I assume that circuit has a single pole response, this is HF square, means a circuit frequency response, squared value. This is a noise frequency response. But suppose a circuit has only thermal noise, it will have a noise behavior, maybe a constant white noise. Okay, so now the noise behavior and the circuit behavior, okay, when they get coupled, how does the spectrum of the total noise will appear at the output? Signal is noise signal. Frequency response is of that of a circuitry. Signal is applied to the circuit. What happens to the output? Signal systems. Signal is the spectrum is shaped by the signal, output signal spectrum is shaped by the frequency response of the circuit. It is shaped by the frequency response. So my signal was having this noise behavior. It passed through a circuit with this frequency behavior. As a result, output has a frequency behavior which is shaped by the circuit frequency behavior. LTI systems, remember, linear time invariant systems. Remember, this is true for LTI systems. Since our circuits, they fall into that category, linear time invariant systems, because they follow all those characteristics of LTI. As a result, noise signal passing through a circuitry with a certain frequency response, output signal has the shape of frequency response of the circuit. So if this is the situation for a CSA, can I find out the frequency response of my output signal? My output signal, how does output signal changes with frequency now? When my signal is a thermal noise signal or a flicker noise signal, or both a combination of thermal and flicker noise. How does the output behavior will change with respect to frequency? This we'll do next time.